I should have your tests graded by Thursday, if not next Tuesday. All right, so now we move into the weird math. Chapter 10 deals with parametric and polar equations. So these are equations that are based on something else. So your x and your y coordinate will both have an equation based on it with parametric equations. All right, so you can see here we've got this cool little squiggly graph. And if you're looking at it, one of the things that you should notice on it is there's little arrows. The arrows tell you the direction of the t. So it's almost like you're adding a parameter of time. So we have, as we're going, we don't necessarily go from left to right. We're going up in terms of the t, and the equations are going to change based on that. So here is a nice, simple example. So have any of you actually seen parametric equations before? Okay, because it's not something, it's like sometimes they do change for Calc, sometimes they don't. It's one of those things like if you get to it, it's great. If not, don't really worry about it. However, this is actually how you can do some really cool things on graphs. You can actually make like those flower graphs and stuff like that are made with parametric and polar equations. So because it's non-linear, you don't have to necessarily, you're not relating the x to the y, you're relating it to something else. So you can actually do some really creative things. So in this case, my x is t squared minus 2t, and my y is t plus 1. So you're basically setting your t like you normally would have set your x. Here's some values for that, and you're plugging them into each one of them. So we have t is -2. If you plug that into the x, we get 8, and if you plug it into the y, you get -1. When I'm graphing it, I'm not graphing in the -2. I'm graphing 8, -1. So that's that point right there. And then we do that same thing going down, -1, 0, 1, 2, and we get this horizontal parabola. Notice the arrows on it tell me how I'm going. So this is a directional graph. So unlike a typical graph where you can go in either direction, you put the arrows at the end, it goes either way. When you're looking at a parametric equation, you have those arrows tell you the direction of it. Yep, thank you very much. Okay. Any questions with how this is done? Would you like to try one? All right. X equals. And we'll use cosine. Come on. And we'll use. All right. So find me my X and my Y. And that's what you should get. You should actually get a half circle. So, because you got the first one should have been -1. Yep. -1 and then 0. Right there. And then it basically would have gone up and over to that. So that's what you would have gotten with it. If you had done it out from to or -pi to pi, you'd have gotten a whole circle. So here's a this is actually a parametric. These are parametric equations. Why is it moving? Because you can actually, in Desmos, you can have your values change. You can rotate your values. So, but this is basically, these are parametric equations. So it's just a bunch of them, and to get the beating, one of the parameters is just changing as you're going through it. This was another one one of my students made, called it the Eye of Doom. This is one kid who really wanted a great grade in his test. So, like, these are all parametric style equations. So that's what I'm saying. Like, this is one of those like really cool type things where you can actually do some cool graphs with it because you're moving outside of the function. Like, it's not a functional equation anymore. It's a parametric equation. Or in this case, actually, is dealing with some polar in there as well. So, but there's some cool things you can do with Desmos to do that type of stuff too. All right. One of the more important style graphs is known as the cycloid. So a cycloid is the graph that is generated by a rolling wheel with a point on the wheel. So if that's my point, as we roll, it goes basically down and then it's moving up. So basically, as the wheel's rolling, if you put a marker on it, that's the graph that it would actually form. It's known as a cycloid. The cycloid, there's a reason I'm showing this because there's a lot of problems that come up about the cycloid. So having the equations for it is actually kind of important. The cycloid uses x equals r, parentheses, theta minus sine theta. So in this case, instead of using t as its parameter, it's using theta as its parameter, which is fine. Okay. Parameter does not have to be t. It just has to be something that is used in each of the equations. And r just stands for the radius of whatever circle you have. So the r is the radius of the circle. So whatever circle you're dealing with, that's the r. So that's a known entity when you're writing the equation. You'll know the radius of it. The thetas and stuff will actually create the actual graph afterwards. That's your parameter. All right. So instead of spending a ton of time going through and doing the parameters because I need this done today, and we have to do all the trig for it. I mean, not the trig. We have to go through and do all the calculus on it. We're going to move on and do the calculus for it. So a few things that we're going to want to be able to figure out when we're looking at any type of equations. The first thing we're going to want to be able to figure out is tangents. So tangents are basically your derivatives. Remember, we're talking about at Calc 1, you're dealing with derivatives. Derivatives give you your tangents. So it tells you how fast something is moving at that point. Unlike what you did originally when they were functions and things, it didn't, you typically went one direction. So it might have gone back and forth when you had the derivative of it, but it was still 1x, 1y. It was a functional equation when you had it. These are not. So to find the dy dx, we have two pieces. You have your dy over dt divided by your dx over dt. So you basically have to do the derivative of each one of them, and you're dividing. Okay. So this will allow us to figure out where the graph is decreasing, where the graph is increasing, where it has horizontal asymptotes. The second derivative will tell me where my concavity changes, no difference. So your second derivative is the derivative of the first derivative divided by dx dt. So the derivative of the x. So it's not the second derivative of the y, the second derivative of the x. It's the derivative of your first derivative divided by the derivative of the original x. Give me a second to finish writing that down, and then we'll use it. So, all right, let's use it. All right, so we have our two equations, x equals t squared and y equals t to the third minus 3t. The first question says, show that C has two tangents at the point 3, 0. So we want to find, so if we look at the graph of this, I'm going to switch back in 1 second. So if we look at the graph, that right there is at 3. Notice how it crosses there twice. They want us to be able to show algebraically or within the derivatives that there's two tangents at that point. Okay? So what would be the first thing we'd have to find? Yeah, let's find what the tangent is, right? Let's find the slope. So let's do our derivative. So the dy over dx, so it's dy dt over dx dt. So what's the derivative of the y? Remember, derivative, not integral. Two t or 3t? It's 3t squared. You bring it down and then you subtract 1. Unlike the integral where you add the 1 in and bring it down. So, and now what's the derivative of the x? Just 2t. All right. So we have our derivative. Now I want to find it at that point. So we need to find the t value that's going to work and give me the point of 3, 0. Because I have to plug in t to find my slope. So what t value is going to give me x is 3? So I have 3 equals t squared. So what does t equal? Square root of 3. So t equals plus or minus the square root of 3. Because remember, when I take the square root, I get the plus or minus version of that, right? Because it could be the positive of that or the negative of that. Now, you have to check and make sure that it's going to give you the 0 in terms of the y. All right, we know it's going to give me the 3, but does it give me the 0 for the y? It should, but you do have to verify that because there's certain values that might not work for both of them. So if we plug in, we have t to the third. So I have the square root of 3 to the third plus or minus 3 square root of 3. What's the square root of 3 to the third power going to give you? Remember, you can move that inside, right? So I'd have 2 3s. I can pull one. I can pull that out, and I still have 1 left, right? So it's 3 square root of 3. Because I have the 3 times 3 times 3. I can pull 1 out, and there's still 1 left. Okay. What's the? It's 3 to the third power. So what's the square root of 27?
No.
Same concept, right? It's square root of 9 times square root of 3. Square root of 9 is 3, and there's a 3 left over. So 3 square root of 3 minus 3 square root of 3 gives you 0. And if I was to do the negative side of this, all that would happen is both sides would change, and it still would be the exact same thing. So both these values work. So I have 2 tangents. Okay? I have 2 t values that are going to give me the exact same point of 3, 0. Does that make sense? Yes? Okay. Let's look at it this way. All right, so my t is plus or minus the square root of 3. My xy is 3, 0. And my dy dx was 3t squared minus 3 over 2t. Okay. So we know there's 2 lines that go. It wanted the equations for those lines. How do I find the equation for a tangent line? So I personally would just use the point slope formula. dy minus y1 equals m x minus x1. Don't make it harder than it has to be. You could do the slope intercept form. There's no point to it. So I have y minus 0 equals plus or minus the square root of 3 x minus 3. So y equals plus or minus the square root of 3, x minus 3. And there's my two equations. Because in this one, you can't really do anything with the square root of 3. It's not like a half or something like that where you can actually calculate it out. You can leave it as is. And that's pretty simple to actually change the slope-intercept form if the teacher really wanted to be a pain. I'm fine with the point-slope formula. It's the exact same thing. It's useful. It gives me the exact same information. All right. Does that part make sense? Yes? Okay. The next part of this question asks you for find the points on C where we have a horizontal or a tangent slope. So we still have our derivative. I don't need to find that again. Still have it. So horizontal slopes are where what happens? Horizontal would be where the tangent is 0, flat, right? No slope. So I want to know when this equation equals 0. So I set the top equal to 0. Okay, that's going to give me my horizontal lines. What about my vertical lines? I would set the bottom equal to 0 because that's when things don't exist, right? That's when I have the vertical one. So I set my bottom equal to 0. And that's going to give me my vertical. So let's solve those. So I have 3t squared minus 3 equals 0. So 3t squared equals 3. T squared equals 1. So t equals 1. Or actually, sorry, plus or minus 1. Because when you do the square root, you still have the plus or minus of that one. And then I have 2t equals 0. So t equals 0. So this is vertical, and that's horizontal. And if we look at the equation for the graph, we see that is also true. We have one vertical right here at the 0, and I have two horizontal ones, top and the bottom. So now the question, though, is we need to find the point for those. So because the question was asking what's the point, find the points on C where that tangent is horizontal and vertical. So we've got our t value, so what do I have to do to find my points? We have to plug that back into the equations, which was x equals t squared and y equals t to the third minus 3t. So we have to plug these points back into those two things to find my points. So horizontal, I've got x equals 1 squared, which is 1. and x equals -1 squared, which is 1. And for my y, I've got 1 to the third minus 3 times 1, which is -2. And then I got y equals -1 to the third minus 3 times -1, which is 2. So my 2 points are 1, -2, and 1, 2. And then my vertical one, I do the exact same thing. So x equals 0 and y equals 0. So my vertical one was 0, 0. All right. So if we look at our graph, we can see those equations. And actually, if I do the y equals and then if I do the y equals have our there were 2 tangent lines there, and then we have our horizontal and our vertical ones. That's what we found so far. So there's like, well, why on earth would anybody actually really care? Previous to computers, even rocket engines, stuff like that, everything moved in a parabolic curve because gravity acts on it. Okay. So once we add in guidance systems to it, they no longer act in a parabolic curve. They now act in a parametric curve because you now have an outside force acting on it. So that is your parameter. So if we're looking at trying to intercept a missile now, it is now a parametric tangent, not a parabolic tangent. How does what missile know where it's going?
Usually it's a satellite.
It's satellite guidance and stuff like that.
So it's better.
Now, yes, I oversimplified the situation, but it's in essence that's what they're doing. So it's like when you're looking at like when we were originally thinking about tangent lines and those type of things, you were looking at trying to figure out intercept points. You're looking at being able to figure out where 2 things are going to be able to intercept at a specific point. A great example of that is now when you're looking at things out in outer space, things work based on gravity. So when we sent the probe, and now I can't think of the name of the probe that we sent to the asteroid to run into the asteroid is moving on an elliptical curve. So when we were sending it, what was the name of it?
The one we're trying to move or the one we're taking samples?
No, the one we were trying to move. We actually ran the actual.
I mean that one, yeah.
Yeah, I can't think of the name of the actual thing we ran into it.
I forgot about that.
So we were literally looking for the tangent. So we were sending something up from Earth, and we had to have it actually meet at a specific point. That was the tangent. We needed to come in at that exact point. So yes, and it moved by just a little bit, so that now that we screwed this up, it'll hit us 1,000 years from now instead of never. And by then, the people who did it will say, I didn't realize that was going to happen. So, yeah. Yeah, that works. I'm not here. I don't want to be here, so get away. That works. Yeah, which is in essence is, if you think of the mean value theorem, where it's like, I know these 2 points. It's like, I know I'm not here. It's like, that makes sense. All right. We're going to skip the concavity just because it's honestly just doing the derivative of that and doing the same thing again. And I want to get into the other calculations that we also do need to know. Because we still need to do area, and we still need to do arc length, and we still need to do surface area. All those wonderful things. All right. So anything to do with tangents is derivatives. Anything we go past that point is integration. So here is your integral for area under the curve. Now remember, we're still dealing with. Oh, I forgot to switch back. We're still dealing with basically almost a variable inside of a variable. So we're still kind of looking at that chain rule use substitution type set. So when we're doing it, you're taking basically the integral of g of t, which is your y, times the derivative of f of t, which is your x. Okay, so you're doing the derivative of x times the y, and then you're taking the integral of that. So it's the
Just flips that.
yeah, which doesn't make a difference.
This is another way of writing it.
So when you're looking at the area under a curve, if I go one direction or the other direction, it'll be the exact same thing because we can't have a negative value of it.
Okay, yeah.
So that's in essence all they did. I don't know why they did that. It's like it's not really useful.
Might just confuse someone.
Yeah, that is very possible.
All they just have to say is that A is not always less than B.
Yeah. All right, so let's look at the cycloid. So here's my equations for my cycloid. So I want to know the area under one cycloid. One arch. So we're going to do the derivative of this, and we're not changing R. All right, we're going to keep R there. So R is going to be treated not as a variable, but as a constant. Okay, so this basically means that the equation that we're going to get, the answer we're going to get at the end, we'll be able to figure out for any radius. So I can now take this and go, okay, if my radius is 5, here's the answer. My radius is 10, here's the answer. It doesn't make a difference. So remember, so we're taking the integral from A to B of g of t times the derivative of f of t dt. This is f of t, and that's g of t. And in this case, it's not necessarily t, it's actually going to be theta. It doesn't make much of a difference. So what is the derivative of that? That's step one. So what is f prime of t? Or f prime of theta?
So just a quick question, will X always be the X?
Yes. So what is that derivative? Yes, and then it's just times r. So it's r times 1 minus cosine theta. Because remember, if I'm doing a derivative, so if I had 3x, or well, let's not do 3x squared, okay? I can say that's the same thing as saying 3f of x is x squared and do the derivative of x squared and just multiply it by 3. So it's the same thing. So we're not dealing with the r. The r is basically then just multiplied by whatever my derivative is going to be at the end. So that's why the r did not vanish in that situation. So I have 1 minus cosine theta. All right, so my integral, if we're going from 0 to 2 pi r, so 0 to 2 pi r, because in essence, one arc is the circumference of the circle. It's one full rotation of the circle. So g of t is r1 minus cosine theta. And then we have f prime of t, which is also r times 1 minus cosine theta, d theta. All right, find me my integral of that. How much you remember? Here, I'll simplify it down a little bit. Actually. Bless you. There. Huh? So sine squared theta minus, or yeah, minus or plus cosine squared theta equals 1. Nope, that's fine, except that's not that. You can't just distribute squared. You have to FOIL first. You are actually going to have something that you can work with, but you have to FOIL first. Oh, because I pulled out the r. I can actually get rid of that r, but it's fine. So I pulled out the r squared. And yes, you will need to know the double angle. You will have to use a double angle rule. So step 1, FOIL out. And now you have to do something with that. So look in your book and find a rule that's going to get rid of the square there.
Chapter 7.
Actually, just look in the back of the book. Oh, yeah, we did do this in chapter 7. 7-2.
One times 1 plus.
Yep.
Cosine 2x.
Yep. Let's see. So that becomes, yeah. That becomes that, which basically becomes 1/2 plus 1/2 cosine 2 theta. So this whole thing goes to 3/2 minus 2 cosine theta plus 1/2 cosine 2 theta. And now do the integral. Now you can do the integral of it. So what's the integral? It's the integral of 3/2. Over 2 theta. That should be the simple one. that should be the easy one. What's the integral of cosine theta? It's just sine. So this is still minus 2 sine theta. And what's the integral of cosine 2 theta? Almost. It's 1/4.
Well, I mean, you just said cosine 2 theta.
Oh, okay. All right. I'll give you that one. Yes, it's 1/2 times, and you have to multiply by the 1/2.
You're inconsistent. It's the first thing.
Yes, you're right.
I counted for the negative side. I got it wrong.
You're right.
I didn't count the half.
You're right. All right. So now I got to plug in my.
The R.
Nope, because you pulled out the R, you don't have to worry about the R. We're just looking at the thetas because we're not going to plug in. We're not going to plug in the R to the thetas. The R is a constant, so we'll just pull that all out. Because the R. So if we're looking, actually, hold on a second.
We're treating R like a
I
constant.
must have missed that.
No, so it's okay. So because we're looking at, so it's from 0 to 2 pi. It's 2 pi R. It's whatever the R is. Since the r is a constant, we're pulling that out of the problem to the front, that's where the r squared came from, right? We can't plug in the r to the thetas because then I won't be able to actually calculate those out. Because the r is not going to matter in terms of what the theta value is. The r was just whatever that's going to be. The r doesn't change the r doesn't change your theta's value. The theta is your the t that's going into it. The theta is your parameter. That r value there is on your x. It has no impact on your the parameter we're plugging in, which is theta.
So you're saying it doesn't change like the shape of
Right.
it, just change the length.
It's going to change the length of it, but that's plugging into the x, so it doesn't matter in terms of what the actual value is. Okay, so right, the x and the y. So in this case, whatever my x was, so let's just say x was r. X was my radius. And my t was 2 pi, that's going to give me my 2 pi r at that point when I plug it into x. If x was theta r,
So you're saying because the x and the y values account for r.
yes, I don't need to have it in my,
So why was it initially in the?
because the r squared was actually in the problem. Like didn't matter when I was able to pull it out. That I pulled it all out.
So if we kept the r squared under the integral,
So you can see,
would we need to plug in 2 pi r for everything?
no,
Okay.
see how they did, yeah,
Not how it works.
huh?
Now the r is still on the inside.
Right. So
2 pi
okay.
is on-
So my range was from 0 to 2 pi of the problem. Once I plugged everything in, I didn't use the r there anymore.
Okay, so the r being inside or outside of integral has nothing to do with
Right. It's the parameter is still from 0 to 2 pi, not 0 to 2 pi r. No problem. But now I got to plug those values in. So if I plug in 2 pi to theta, what's r to r squared times, or r over 2 times 2 pi is just 3 pi. What's sine of 2 pi? No, sine of 2 pi is 0. Times -2 is 0. And then sine of, well, in this case, it'd be 4 pi is also 0, right? Yes. Because it repeats every 2 pi. All right, so now what's 3/2 times 0? Is 0. So we're plugging them in, we're plugging these in. Okay, I will write these all out so people can see. Okay, so 3/2 times 2 pi minus 2 sine 2 pi plus 1/4 sine 4 pi minus 3/2 times 0 minus 2 sine 0 plus 1/4 sine 0. So r squared, that's 3 pi, right? That's 0. That's 0. That's 0. That's 0. And that's 0. So my answer is 3 pi r squared. So for any value r. So basically the area under one arch of a cycloid is 3 pi r squared. Always. And if I wanted 2 of them, I would just multiply that by 2. If I wanted 3 of them, I would multiply it by 3. So you go, how much of your car's wheel well will be destroyed if you drive with a boot on? That will create a nice cycloid. I was watching Parking Wars the other day. It's in essence, it would make a perfect cycloid. The end of the boot's going to come up and destroy everything in your car and make a perfect cycloid. Random things we watch on TV, and then just like, oh, that works.
That's what they said in the.
No, I was looking at the shape, and I'm like, wait, that's exactly what the boot does. Huh? Oh God.
I love workaholic. So
Oh.
like, if you have a lifted truck, you're pretty much immune to a boot. Because there's nothing for it.
It's nothing. It's not going to destroy anything on your car. However, at some point, it's now going to go down into the ground and lift your truck even higher. So it probably, yes, it's probably not going to necessarily destroy the wheel well of your car. It'll probably destroy suspension as it's going over.
Attach 3 more boots and then we'll equal out.
Yes, you just need boots on all your tires. And then you have high heels on your lifted truck. All right. I'm just going to do this because I don't think we actually need all the rest of the stuff. And you guys are going to go, wait, that's way too much extra stuff. So don't even worry about, all you literally need to write down is that. That is the formula for arc length.
What is it called?
Arc length. That's the formula for arc length. So, but
Oh. That's- what is it?
this is not a cycloid now. No, it's just it was just trying to show you how you could estimate the length by taking the points and doing, and it's like the integrals is basically going to give it to you smaller and smaller. Now, one of the cool things about the arc length formula for a parametric equation is it doesn't matter the direction it goes. So if this was just say this was a function and giving it to me in terms of f of x, which I know it's not. But if the equation went back on itself, you would have had to break it down your integral. So look at each of those individual pieces. Since I have a parameter and I'm doing everything based on the parameter, I don't have to worry about it going back. When I do the arc length from here to here, it gives me the entire arc length of the entire thing, even though it goes backwards. Because the parameter is still going in one direction. Does that make sense? No.
Parameters.
Yeah, in essence. So like remember the whole if we look back at the very beginning problem. All the way back. See how time is this is going in one direction. So that's just a function. So if we look at that in terms of t, it's going in one direction. So if I'm going to find the arc length of this, it's going to give me, even though from here to here, technically I didn't travel anything on the x-axis. But if I found the arc length of this, it's going to give me that entire length. And I don't have to split it halfway and go, okay, I'm going to go from here to here and then go from here to here. I don't have to do it once, which is, yes, you're measuring the length of the parameter, not necessarily time of the parameter. We like using t as and think about it in terms of time, but it doesn't necessarily have to be time. As we saw in the last one, which was theta, which that wasn't time.
So we can like do it 3 adventures then.
Yeah. And then doing X, Y, and Z. Yeah. Yep. You'll do it at some point. All right, so let's find the arc length of this problem. So remember the formula? So the dx dt and dy dt are the derivatives of those. So x prime is 6t minus 3t squared, and y prime is 2t minus 2. Any questions with that? All right, so now we got to plug it in. So, oh, I didn't give you the actual t values for this. Hold on a second. Actually, I don't think they gave you the t values. I think we got to find them. We're gonna have to find them in this case. Yeah. So, all right. So, what's the t value that's going to give? So, this one right there is 3, 4, and this one is 0, 3. Oh, sorry, 4, 3, not 3, 4. So basically, we're looking for the two t values that are going to give me 3 for y. So I have 3 equals t squared minus 2t. So t squared minus 2t minus 3 equals 0. So I've got, what's it, t minus 3 and t plus 1. So t will be 3 and negative 1. And then we have the square root of 6t minus 3t squared plus 2t minus 2 squared. All right, questions on how, so the derivatives, I don't think anybody had questions on. How did everybody understand, see how I found the t values? Okay.
Is it only exclusive to the y value, or should you have used the x?
You could have used the x, but you would have had to do it twice.
Oh, okay.
And technically, yes, I should have plugged them into the y to the x to make sure I got 0 and 4. But if I plugged in 1 or 3 to that, we get 3 squared. Yeah, that's going to be 0. So, and if I plugged in 1, or -1, I'm going to get 4. So you could plug it in there to make sure you get those 2 points. Yeah, you could have plugged in 0 for the other one and done it out that way too, and you should have gotten the same thing. But it's easier this way. All right, so now let's find the integral. What do I got to do first? Well, I got to clean up the inside before I do the outside, right? So we're going to do a bunch of algebra. So we've got, let's see. So I got 36t squared minus 36t to the third plus 9t to the fourth. Plus 4t squared minus 8t plus 4. So we've got 9t to the fourth minus 36t to the third plus 40t squared minus 8t plus 4. Oh, this is going to suck. I don't think we can actually factor that. Hold on. I don't think we can factor that. At least I don't see a way to factor it right now. I'm going to find out in a second, though. Third 40x squared minus 8 plus 4. So we have our integral from -1 to 3 of the square root of that big mess. So what do we do when we can't integrate it or can't do the square root of it? We use decimals. Now, me personally, since I got to that point and I know I can't factor it, if I'm plugging this into Desmos, I'm plugging that into Desmos. Why would I do that? In case I screwed that step up. Exactly. So go back to the place that you know is correct in case you messed up anything after that point. Because I have to use Desmos for it anyway. It makes a lot more sense.
So it was the last red line, correct?
Yes. But since I have to basically go back into Desmos and type to do the integral anyway, I'm just going to go back to the one that I know is absolutely correct, where I didn't mess up a sign or anything else in there. So it's one less thing that you have an issue with. The -1 to 3 square root 6x squared plus so, and you should be able to, let me just make sure. You should be able to actually do these in terms of t. So you do not have to do this in terms of x. You can do it in terms of t. Just whatever you're going to do or take the integral of has to be your d at the end. So since I did it in terms of t, it's got to be dt at the end. So in this case, my arc length is 15.21.
How many decimals back do you want to say?
Two.
Just two.
It's fine. 2 is fine. In all honesty, it depends on what you're doing in terms of, like, if it's a word problem or something like that, depends on how much accuracy you can have in the problem.
Yeah, it's just an,
And this, if it's just a simple problem, 2 is fine.
teacher.
Yeah, 2 is fine.
So if you're using like meters or units, down to 3 decimal places, it's like.
Yeah. Yeah, it's literally a millimeter. Yeah. If you're doing millimeters and down to 3 decimal places,
Inches.
yes, it's tiny. Yes. Yes, it's very small. All right. One more equation to go. Surface area. The formula should look really similar. It's just the arc length times the rotation, the 2 theta or 2 pi times y. The only difference that would come up in this is, again, depending on which direction you're rotating, you could do the y or the x there. Remember, that's your radius. Okay? So this value right there, that's radius. So if we're going from the x up, my radius is y. If I'm going from the y over, my radius is x. And that would be whatever equation you're going to have. So unlike before where one of them was going to have an equation, one wouldn't, in this case, they're both going to have an equation. Because you have an equation for x and you have an equation for y. All right, so the surface area for a sphere is 4 pi r squared. Okay? That's the surface area for a sphere. We just want to prove it. Well, in actuality, this is where this formula came from. So the calculus came before this formula. Before this formula, they estimated it, but they didn't have an exact value. So once calculus came in, then they actually were able to come up with the exact formula for it, which is what we use today. So it's just like trying to square a circle. Like they could estimate, get close to it, but it's not exact. So I gave you the formula for the circle earlier. Anybody remember what it was? Nope. What was the x and what was the y? The 3 pi r squared was the cycloid. What was the problem that I gave you at the beginning of class that gave us a circle? Yes, but which one was which? X was that. I'm almost sure I put the x was sign. Yeah, the x was sign.
All this with the tree stuff because the X was always cosine.
Yeah, I was just saying it's based on what I did.
Well, would it really matter?
It doesn't actually. But since I already gave it to you, I was going to use what I did. But yes, it doesn't actually matter in terms of the problem. If I switched them, it wouldn't make a difference because we're going to rotate the whole thing around anyway. All right, so we did this from, I've got this half circle here, and I'm going to rotate it all the way around, right? So we're going from negative pi over 2 to pi over 2. And we're rotating this around the x-axis, right? So I've got 2 pi. My y is going to be that, so cosine theta. And then I do the derivative of each one. Oh, I forgot one thing in this thing. Because we're doing the general form, I forgot I have to multiply this by the r. Because we were doing the general form. Yeah, because the r is going to be but we're going to have the r inside here too, which is why I did that. So the derivative of r sine theta is what? R cosine theta squared plus the derivative of r cosine theta negative r sine theta squared. So over here, I can pull out the 2 pi r, and I have cosine theta left out front. In here, I have r squared cosine squared theta plus r squared sine squared theta. If I pull the r squared out because it's the same, what's cosine squared theta plus sine squared theta? 1. So that whole piece right there is 1. So it's just the square root of r squared, which is r. So I have r cosine theta, d theta. I'll pull out the other r in a second. All right, so I have 2 pi r negative pi over 2 to pi over 2 r cosine theta d theta. I can pull out the other r. What else can I do with this? The negative pi over 2 to pi over 2? It's still symmetric, right? Yeah, I can just do it to 0 and then double that, right? So I have 4 pi r squared from 0 to pi over 2. And then I just have cosine theta. So what's the derivative of, or the integral of cosine theta? Sine theta. You're ahead of the game. And we're valuing this from 0 to pi over 2. So I have 4 pi r squared. Sine of pi over 2 is 1. Sine of 0 is 0. So the answer is 4 pi r squared. So I took, instead of going from negative pi over 2 to pi over 2, I used symmetry. And I said I can go from 0 to pi over 2. So I cut it, the interval in half and just doubled the answer because it's symmetric. All right. Any questions? Okay. We are done. Thursday we do polar. And we're basically gonna do the exact same thing. Just with the polar equations. So
So, so for the next, is this chapter, next one, next class is learning the basics?
no, that's it.
Is that-
We're gonna be done with chapter 10 this week.
Oh,
The chapter 10 is literally parametric, polar. There's some other stuff after it, but those are the two things we cover in chapter 10. So that's 10.1, 10.2. This was 10.1 and 10.2, and then polar is 10.3 and 10.4. And then next week we go into chapter 12, which is vectors. So in essence, this is all your, as he was saying, kind of three-dimensional stuff. It's dealing with multiple variables because the vectors are actually going to look at 3 dimensions.
okay, so,
So it's kind of moving you past just a simple XY concept.
so is there, this is taught before, before 11?
Yes. I don't do it before 11, but yes.